Newton's second law of motion. So this is the mathematical one. This is where we express force and dynamics as a mathematical equation. And that mathematical equation is a simple one, which is, I'm just going to go down to the bottom here. It's very simply this behemoth of a formula, F equals ma. The force equals the mass times the acceleration. And some people put net force here, which is a good idea. Net force equals mass times acceleration. Therefore, the permutations of this are acceleration equals net force over mass, and mass equals net force divided by acceleration. The one that appears on your formula sheet is, is this one. This one. Now, why does that one appear on your formula sheet? This is a good formula because it shows you the relationship between mass and acceleration and net force and acceleration. And what it shows you is that the acceleration is directly proportional to the net force, and acceleration is inversely proportional to the mass. And these are terms we're going to use with increasing regularity in physics. Directly proportional to, inversely proportional to. If something is directly proportional, it means that one value goes up, the other value goes up. So in other words, if I increase the net force on an object, then it's going to accelerate at with a greater magnitude. So that's what directly proportional means. A is directly proportional. Looks like a fish, the little infinity symbol, a half an infinity, 3/4 of an infinity symbol. A is directly proportional to F net. For the mass, it's inversely proportional. So meaning that if the net force on an object stays the same, but I increase the mass, then logically the acceleration is going to decrease. So we say that acceleration is inversely proportional to mass. Acceleration is inversely proportional to mass. If I increase the mass, I will decrease the acceleration, assuming the net force stays the same. I can also read this as acceleration is directly proportional to 1 divided by the mass. And that's going to become more important as we do graphs. So for example, if I was graphing mass and acceleration, and I'm assuming the net force stays the same, then what's going to happen as the mass increases, the acceleration decreases. So I get a graph that looks like this. But if I want to linearize that graph, make it into a straight line so I can find the slope and find out something useful about these pieces of information, then I would have to do this. I would, instead of graphing m on the x-axis, because I just said in my previous statement, I said that right here, A is inversely proportional to m, but I also said that A is directly proportional to 1 over m. So if I can say they're directly proportional, then I get a straight line. So if I graph 1 over m, then I get a straight line. All right, we're getting a little ahead of ourselves here, but this is all going to be important, especially for physics 30, when the linearization is a more important concept. Okay, so here we go. You can read over your notes. I've kind of just explained all this, and here's the relationship stuff. Relationships important. The little swimming fish symbol is a Greek letter alpha. It means varies as. It does not mean that they're equal. So it just shows a relationship. It shows that if one is increasing, the other is increasing, or if one is increasing, the other is decreasing. Okay, and then here we go. Here's the formula which you normally see it in. Again, I'll remind you that on your formula sheet, it looks like this. Okay, they're obviously the exact same formula, and because this is such an important concept, and because Newton was such an important man, we decided that kilograms, the units for mass in kilograms, and the units of acceleration are meters per second. So, but instead of writing meters per second squared for force, we've decided to just abbreviate that and call it newtons in honor of the great man, Sir Isaac Newton. All right, but then here's a good definition that you should probably be aware of. By definition, 1 kilogram mass will be accelerated at 1 meter per second squared if 1 Newton force is applied to it. Example number 1, nice, easy one. Determine the force acting on a 5.46 kilogram object if it's accelerated at 17 meters per second squared. So, by going from the formula sheet, then I'm going to see this, and then I'm going to have to rearrange that formula. F equals MA, because I'm trying to find that force. I know that the mass is 5.4. I know the acceleration is 17. I simply multiply those two numbers together. And I don't have my pen. So later, 5.46 times 17 is 93. 93 newtons. 93 kilograms times meters per second squared, which is 93 newtons. Example number 2 is also pretty easy. It says determine the acceleration. This is great because that's how the formula appears on your formula sheet. If a 1,000 kilogram car, or a 1,000 kilogram car, a force of 2 times 10, it's going to be 3 Newton force X on it. So well, that's pretty easy. It's just going to be 2.5, isn't it? 2.5 times 10 to the 3 is 2.5 times 1,000. And so those thousands are just going to cancel out. So what's the acceleration of the car going to be? 2.5 meters per second squared. Okay, now let's move on to something a little more engaging, because that was way too simple. Applications of Newton's second law, and there are a lot of applications. We'll probably do 1 or 2 of these, and then we'll start the video again to do the others, or else it'll be an excessively long video. So it's best to start with the more complex diagram by analyzing what forces are involved, come up with the net force formula, and then draw a free body diagram. So in our first example, we have an elevator being raised by a cable. It gives you the mass of the elevator, and it gives you the force acting on the cable. Determine the acceleration of the elevator. So there's a free body diagram over that. I'm going to draw mine over here, because why not? We have the force of tension, the tension of the cable, pulling the elevator up. We have the force of gravity pulling the elevator down. And this is why free body diagrams are really important, because every free body diagram is going to be a little different. Those are the two forces acting on it. It's actually a pretty simple problem to start with. The F net, the net force, is the combination of those two forces, the force of tension and the force of gravity. We're given the force of tension right here, 4E4. The force of gravity we have to calculate because we know that Fg equals mg, so plus m. Now, we have to acknowledge that these forces are in opposite directions, so one has to be positive, one has to be negative, and that manifests itself as soon as we put in the negative 9.81 right here. The negative 9.81, that's going to make this entire value in yellow. Oh, it's supposed to be yellow. That's going to make this entire value negative, so that accounts for the opposite signs. If the force of tension is positive, then the force of gravity must be negative. By having this little negative right here, that makes that negative, and we're good to go. And the answer turns out to be, for the net force, that is, the net force is 4E4 plus bracket 3.7 E3 times negative 9.81, and the brackets equals 3,703 newtons. Now the question is not asking for the net force, it's asking for the acceleration. So we'll call that step 1. step 2. Ooh. Step 2 is just going to be to find the acceleration. The acceleration equals the net force divided by the mass. It's going to be about 1, isn't it? Which equals 1.0008. So just 1.0. 1.0. Ah, I knew I wouldn't get away with that. 1.0. Now, the answer is right here. 1.0 meters per second squared. Okay. Now, example number 2 says determine the acceleration. Or number 6. Acceleration of the elevator. For example number 5, the detention is only 3.3 E4. Okay, so it's exactly the same problem. We're gonna the only thing that's going to change is this number right here. Right, that's going to be a 3.3. This one I'm going to show you how to do it in one step, just so you have the knowledge of both. And if you're doing it in one step, you would do it like this. You would say that F net equals Ft plus Fg. But then you would change your F net into MA. MA equals Ft plus Fg. And you're solving for accelerations. You divide both sides by m. Divide both sides by m. So you end up with this. A equals Ft plus Fg divided by m. And if you look at the previous example, you can see logically this is what you end up doing anyway. You add the two net forces and then you divide by m, which is exactly what we did in the previous question. This one's just a little different in that the tension is now only 3.3 times 10 to the 4. Oh, I'm already down here. Otherwise, that nasty thing is going to happen. 3.3 times 10 to the... No, it wasn't 4, was it? I've already made a mistake. No, I haven't made a mistake. It's times 10 to the 4 plus Fg equals mg, and the mass 3.7 times 10. No, I forgot. What was 3.7 times 10? 10 to the 3 times negative 9.81, and then divided by the mass 3.7 times 10 to the 3. And you stick all that into your calculator, and what do you end up getting? You end up getting negative 0.89 meters per second squared, and the negative simply means that it's going down. It's accelerating down. If the tension in the cable is less than the force of gravity, the gravity is winning, and the elevator is going to accelerate down. It doesn't mean that the cable is going to break. Accelerating down. So the elevator is going down. All right, it's already been 13 minutes. We'll stop here and then we will continue with this lesson, part 2 of net force Newton's second law.